Hello and welcome for Real Analysis Day 1. So the first thing that we're going to start off with is we are going to start shaping our understanding of the real numbers, and eventually we can expand that out. But our understanding of the real numbers is going to be very important here because we need to get concepts like if there's holes in the set, holes, I'll put in quotation marks, or things like this, that's going to be important to our understanding in the future. So if we need to know when there are when something is we can call something complete. You'll see the definition of that later on in the course. And these kinds of things. So it's going to be very important to understand what's going on in the real number line so that we can carry forward throughout the course. And obviously this is real analysis, so we're going to be focused on real numbers. But none of what we're doing here what we're doing here could be expanded out to other fields like the complex numbers and things like that. But we will start off by getting at sort of the nitty-gritty of the perhaps the most confusing part of the real numbers, which are the irrational numbers. So you know that for a rational number, we kind of have some kind of solid understanding of rational numbers. The irrational numbers, though, let's start with this sequence, and we'll get into what I'm trying to get at. Maybe not describing the greatest at the moment, but trying to get at here. So let's start with this sequence. We have the sequence that goes 1, 1.4, 1.41, 1.414, 1.4142, and so on. This is tending to some number, right? Like as we give more and more digits, it's getting closer and closer to some number. No problems here. This happens with rational numbers as well. We can have a sequence of numbers that gets closer and closer to a rational number. But what happens if this sequence gets carried out to an infinite number of digits? Well, this actually tends to some number, as we'll see, that is not a rational number. Okay, so this sequence actually tends to the square root of 2. Now, how do we know that this is not a rational number? Well, we have to have some way of proving that it's not a rational number, and that's going to be sort of a key thing that we'll be doing throughout the course. What exactly is the square root of 2? Well, let's show that it's not a rational number. Where do we even start with that? Well, we start with the definition of a rational number. So recall that what a rational number is. A rational number is any number that can be represented as an integer divided by another integer. Okay, so we're going to use that to our advantage. So we'll start off with a rational number p. And if the square root of 2 is rational, then we could square both sides, and we can see that this rational number p squared has to be equal to 2 if I square this. So we're assuming that p is rational. Since we're assuming that p is rational, then there must be an m, of a number m, which is an integer, and a number n, which is also an integer. So when I say this z here, I'm talking about integers, such that p is equal to m divided by n. So we would say that p is equal to m divided by n, and m and n are integers. So we can, because of the definition of a rational number, so then we can square it, and what we'll get is m squared over n squared must be equal to 2. Now, we're going to make one additional assumption here. We're going to assume that P is written in its most reduced form. And what I mean by that is that we've taken out any any common factors that they have. Since the two numbers m and n, we can always do this with rational numbers, right? Any rational number can be written in this way. Since we are going to take out any common factors, then we know that, with the exception of the rational number 1, right? We have to be careful about that, I guess. But since this is not equal to 1, we know that that's the case because 1 squared would be 1, not 2. Since we can reduce this into, we can put this into its reduced form, and it's not equal to 1, then we know that the number m and the number n cannot both be even. That's not possible, right? Because then if they were both even, we could just take out a factor of 2. We could just remove a factor of 2 there. So, since that's the case, then we're going to say, okay, we cannot have both m and n be even, and and p is equal to m divided by n. Great. So we're starting out with this. Now we're trying to prove that this is not a rational number, and so I'm going to tell you that the course of action here is we're going to try to search for a contradiction. And the contradiction, just foreshadowing here, is going to be that we start off by saying m and n cannot both be even, and then we're going to show that they must both be even through the course of this, which is a contradiction. Okay, so let's follow through with the logic here. Since we could write p as m over n, we already saw that means m squared over n squared is equal to 2. Now I can rearrange this, so n squared comes over here, and we get m is equal to 2n squared. Now, because m squared is going to be an integer, right? Because if I square any integer, I get some other integer. So because m squared is an integer, and it's a multiple of 2, right? Because I have 2 times n squared, and n squared is also an integer, then m has to be even. M squared has to be even. And we can work backwards from m squared and see that m has to be even as well. If any number, if we square any odd number, we get an odd number. So the fact that m squared is even implies that m is even. Great. So we've shown that m is even. So now, if we didn't want a contradiction, we would have to show that n is not even. But we're going to see that n is forced to be even in a moment. Okay, now, since m is even, then we know that if we were to square it, right, so it has some factor of 2 in it if it's even, right? Then if we square m, it's going to have a factor of 4, right? Because since it has a factor of 2 in it already, then it would have to have a factor of 4 in it if we squared it. Great. That means that we can divide m squared by 4, right? And we would still get an integer. So if I come down here, I'm going to divide both sides of this equation by 4. Doing so is equivalent to multiplying by 1, right? So we haven't changed anything. M squared divided by 4 has to be an integer because we already mentioned that we know that it's divisible by 4 because of the fact that m squared, if m was even, it has a factor of 2 in it. Squaring it, it must have a factor of 4 in it. So we know that m squared divided by 4 would have to be an integer. And if we divide by 4 on the other side, remember we had 2n squared here, so dividing by 4 gives me n squared over 2. Now, since the left-hand side has to be an integer, m squared divided by 4 is an integer, we already have established this, then n squared divided by 2 also has to be an integer, right? Because it's an equal sign. And the only way that n squared divided by 2 is an integer is if it's even, right? Because dividing by a number by 2, giving you an integer, requires that that number be even. So that means that n squared was even, but then following that same logic that we had before, that means n is even. So we've now shown that both m and n are even, but at the beginning we were assuming we were writing this in its reduced form, and we said m and n could not both possibly be even, so we've arrived at a contradiction. So this proves that this is not a rational number. Okay, so we actually have some number that lives outside of the rational numbers, and this is the square root of 2. In fact, as we'll see at some point later in the course, in some ways you could think of the rational numbers as being an even bigger set than the rational numbers. We'll be able to show this at some point in the course. So there, once we have some idea of measuring the size of sets, we'll be able to do this. But in any case, we've shown now that the square root of 2 is not rational. And I mentioned this idea of wholes in quotation marks. So basically, this actually, as we'll see in a moment, shows that the rational numbers have some sort of holes in them, if you will. There's spaces in between the rational numbers that get filled by the irrational numbers in the real numbers set. So how do we show that there are these holes? Okay, how do we show that there's gaps in between the rational numbers? Well, let's start off with, we can start the square root of 2. We can actually show that the square root of 2 is sort of sits in one of these holes. Let's start with that. Why not do that? Okay, so let's choose A to be the set of all rational numbers such that it's bigger than 0 but less than x squared. You know, the rational number squared is less than 2, right? And this should be reminding you of the square root of 2, right? If I took the square root of all sides of this, then I would see that x is going to be less than the square root of 2, right? And in order to do this, similarly, I'll choose a set B to be the set of all rational numbers again, but that are greater than 2. So we're trying to see, is there a rational number that sits in between, sits around square root of 2, right? Essentially. Well, we can start off by saying that A contains no largest number and B contains no smallest number, right? Because A is a set of rational numbers, and we already saw that the square root of 2 is not contained in A, right? And in fact, and it's also not contained in B, because we already showed earlier that the square root of 2 is not a rational number to begin with. Okay, good. Now, we can actually go through and show that A has no largest number by choosing a rational number Q, which relates to P in the following way. Okay, so it's going to seem weird why this is chosen like this, but you'll see why it's convenient in a moment to choose it like this. So we're going to write Q as P minus P squared minus 2 over P plus 2. Okay, now the first part of this is maybe kind of clear why it was chosen, the P squared minus 2. Well, remember that P squared being less than 2 excuse me, relates nicely to the square root of 2, right? So if I then take this and I say p squared minus 2, well, that means it's going to be negative if we're dealing in the set A, right? The set A is this set. It'll be equivalent for B, except for p squared minus 2 in if it's in the set B will be positive. So this is the beauty of these two sets. If p is a rational number in A, then this relationship has to be negative. If p is a rational number in B, then this would have to be positive, this p squared minus 2. We'll see why that's useful in a moment. But anyways, so that means if that's the case, then Q has to be bigger than P, right? We can already see this right away, because since p squared minus 2 is negative and p is greater than 0, right? In both of these sets, we can see, but we're dealing with the set A right now. So in this set, we can see that p has to be greater than 0. So because p is greater than 0 and p squared minus 2 is less than 0, then there's no way for this term over here to be less than 0. There's no way for this term over here to be greater than 0. And because of the fact that it's negative, when we subtract it off, it's gonna mean that Q has to be bigger than P. Okay? Great. So we've established that Q has to be greater than P here. Okay. Now you might say, okay, well, why did you divide by the P plus 2? Well, we're going to see in a moment that actually helps us show that Q is also in A. So even though Q is greater than P, it's still in A, which will mean that A contains no largest number, because we can always choose some value Q that's bigger than the current value of P, right? So this is what we'll see. So what that means is we can use Q squared minus 2, right? Well, we defined Q this way, so this is going to require a lot of algebra, and you'll see the algebra in a moment. I'm gonna work it out for you. Q squared minus 2, well, if Q squared minus 2 is less than 0, it has to be in A. We already discussed that this was the case for P squared minus 2, right, is in A. So Q squared minus 2, if it's a rational number, which it has to be because P is rational, then it's going to be inside of A. Okay, so great. So let's actually do the algebra out. The book doesn't do this, but so I figured that it would be useful to actually work this out, and we'll be able to see that everything works out nicely. So if I square Q, right, I take this definition up here and I square Q, I get this. I get P squared minus 2 times P times P squared minus 2 over P plus 2 plus P squared minus 2 squared over P plus 2 squared. So basically, I'm just taking this P is the first term, and this other thing is P squared minus 2 over P plus 2 as the second term. And if I square everything, then I get all of these terms. Looks pretty ugly because it is. Now what I'm going to do then is I'm going to put, and we'll see why in a moment we do this, but it should be kind of clear at this point because of this P plus 2 term under here. I'm going to put everything in terms of the denominator being P plus 2 squared. And if I do that, then you can see I get a whole bunch of ugly terms, but a lot of them end up canceling out. Okay, and so what I end up with is this. I get Q squared is equal to 4P squared plus 8P plus 4, and I encourage you to try this on your own, but plus 4 divided by P plus 2 squared. Great. So now I've expanded it all out, and I get this term. Now if I subtract off 2, well, when I subtract off 2 from the left side, if I subtract it off from the right side, I'm also going to put it in the same denominator to make my life easier. So it's going to be minus 2, but then I want it in the denominator p plus 2 squared, so I have to multiply then that 2 by p plus 2 squared as well. And long story short, I get more cancellation if I do this. So it comes down here, and it becomes 2p squared minus 4 over p plus 2 squared. And finally, I can rewrite this. So I get 2p squared minus 2 times p squared minus 2 over p plus 2 squared. But notice that, first of all, p is greater than 0. So that means that this whole thing down here squared has to be greater than 0. But the numerator is less than 0 because, again, remember that p squared minus 2 is less than 0 if p is chosen from the set A, right? We already know this to be the case. So that means that this is negative. This whole thing is negative. So that means that q squared minus 2 is less than 0. This is less than 0. Which implies, we also know that this is in Q. In the rational numbers. So this implies that Q must be in A. So since Q is in A and Q is greater than P, we can always choose a number that's greater than, we can always choose a rational number that's greater than whatever rational number we've chosen, P. So we can always keep going. We always get a bigger and bigger and bigger number. So that means that you can kind of see that this implies that there's some hole here, because I can keep choosing some number from the rational numbers, and it's going to always get bigger, but it's always approaching something. And in this case, it's approaching the square root of 2. But I never actually reach that number, right? Because I keep choosing a bigger and bigger and bigger number that gets closer and closer to this, but it never actually reaches that. So it never fills in that sort of hole in the number line, right? Great. We can do the same thing for B, the set B, except for we flip the sign. And essentially what you'll find is that we can always get smaller, 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 still in B, but we never actually reach the number being obviously the square root of 2 there. So, so there is no lower bound in B either. Great. So this just shows that there are these holes in the rational numbers. And when we fill out the whole real number line, the irrational numbers fill in those holes, basically. So there are no holes in the real numbers, but there are holes in the, so we can always choose. This is nice, and we'll see in the real numbers what this leads to, basically. That's what this whole next part is, the ordered sets, and we'll be talking about supremums and infimums in a moment. And the fact that we can have these in the real numbers is extremely useful, but we don't have this property in the rational numbers. So we actually, zooming out to the real numbers is useful, because we're going to end up with a whole bunch of properties that we wouldn't get if we only had rational numbers. And obviously, by the way, the rational numbers contain other numbers in them, right? So the rational numbers contain the integers, as an example. So the integers are contained inside of the rational numbers. And similarly, the natural numbers are contained in the integers, which then are contained inside the rational numbers. So we can actually build up these sets until we reach the real numbers. So the real numbers contain the rational, the integers, the whole numbers, right? And they also contain another set called the irrational numbers. Great. Now let's talk about ordered sets. So this is a very useful property that the real numbers have. So let S be some set. It doesn't have to be the real numbers, but let S be some set. An order, this is the name here, an order on S is a relation. Okay, so you can scroll out and remind yourself of what a relation is. It's similar to a function, but it's not necessarily a function. So just keep that in mind. But we have a relation. We're going to denote it by this symbol. We typically think of this as the less than symbol, and for this course, that's what it's going to be. But that less than symbol might not mean less than in other contexts, right? So in the real numbers, it's going to mean this. Mean the traditional thing that you've learned throughout all of your mathematics courses up to this point. And this symbol, this less than symbol, has the following two properties. If x is an element of the set x, S, excuse me, and y is an element of the set S, then only one of the following statements can be true. Either x is less than y, x is equal to y, or y is less than x. Only one of these can be true. You cannot have that x is less than y and it's also equal to y, right? It cannot be both of those at the same time. So if we choose a value for x, we choose a value for y, it's not possible that the value of x is less than y and equal to y at the same time, right? Or that x is less than y and y is less than x. You can't have both of those be true at the same time, right? So only one of these three properties is true. The second thing that makes this an order on S is we have this transitive property. Basically, if I have x, y, and z in that set, then if x is less than y and also y is less than z, this implies that x is less than z. This seems kind of trivial. This is what you've learned, but we're trying to build up from first principles everything. So we are trying to start off with as few assumptions as humanly possible and build things up from that. Okay, so x is less than y, y is less than z, then that implies that x has to be less than z. Okay, so if those two properties hold, if we have the fact that only one of these statements is true, and we have the transitive property that we have here, then there is an order on the set S. So you can imagine sets that don't have an order, right? If you had some numbers as an example, just going directly to the complex numbers, well, how do you know if I have x being a complex number, that x is I have two different complex numbers? How do we know that one is bigger than the other? We don't. We actually then need to add some additional structure in order to recover the ordering in that case, right? Simply drawing two complex numbers, I can't order them because I don't know if 1 plus I is less than 2 plus I. I can't say that is true. in the complex numbers. I need to actually add some additional structure, at which you would do in a complex analysis course. I would need to add some additional structure to it in order to create an ordering of those numbers, right? But here I naturally get the ordering, right? We know that if in the real numbers we get this natural ordering, which is nice. Okay, so now we're going to get a bunch of definitions. So an ordered set is a set S which has an order defined. So this is very nice. For example, Q is an ordered set. So Q being the rational numbers, by the way. Q, every time I say capital Q here, I'm talking about the rational numbers. Q is an ordered set if we take R less than S to be defined to mean that S minus R, so if I were to move this R over here, subtract it over, that S minus R is some positive rational number, right? Well, of course, right, if I move S minus R, if R is less than S, then that means S minus R is greater than 0. So it's got to be positive, right? This is all that we're saying here. Okay, great. So an ordered set is a set S which has an order defined on it. Great. Now, suppose we have another definition. Suppose S is an ordered set. Okay, so we already have figured out a way of ordering the rational numbers. And we also have that E is a subset of S. So we have some set that is a subset of S, which means that all of the elements of E are also in S, right? Every element in the set E is also in the set S. Great. If there exists some number beta in S such that it is it is greater than or equal to all X in E. So now we have the set S. We know that we can pick a number out of that set S that is bigger than or equal to every other number in E. Then we say that E is bounded above. So we're gonna be talking about bounds now. We say that E is bounded above, and we call beta that value, that number that is greater than every number in E, the upper bound of E, an upper bound of E. I shouldn't say the upper bound, because the problem with that is that there can be infinitely many upper bounds. So I made a bad mistake there in language. It's an upper bound, because any number bigger than beta is also an upper bound of E, right? So we can also call it bounded below if we flip these signs here. Basically, if every number, if we have a number that's less than every number in E, then it has a lower bound that we could call gamma or something like that if we wanted to. So I made this note here, fixing my language that I almost made the mistake of there. There is often an infinite number of upper bounds. Not that there's not, we could have some finite set, right? But that acts as upper bounds. But often there is actually an infinite number of upper bounds, right? Once I choose some number beta and I set that to be the upper bound of this set, then any number bigger than beta, so we could, if we carry it out to infinity, if that set S is, say the real numbers, and we carry it out to infinity, then there's actually an infinite number of upper bounds, right? Great. Now let's do another definition. So we're going to say, why do we need all these definitions? Because what we're going to eventually do is we're going to start proving theorems, and we have to have some definitions in order to prove the theorems, because we have to say exactly what it is that we're talking about. So we have to have this concept of an upper bound. We have to have this concept of lower bounds. We have to have this concept of ordering and all of these things. Once we have all of those concepts, then we can make some statements and prove those statements based on these definitions, right? Okay, so now suppose S is an ordered set. E is a subset of that S, and E is bounded above. Suppose additionally that there exists some number in S, we'll call it alpha, with the following two properties. Alpha is an upper bound of the set E, so alpha's in S, it's an upper bound of E. If gamma is less than alpha, then gamma is not an upper bound of E. So we have some value, we can choose some value, any number smaller than alpha will actually not be an upper bound of E. Then alpha is called the least upper bound, right? It's the smallest possible upper bound, the least upper bound of that set E, and we'll write it as the supremum. So the least upper bound, the LUB, is also known as the supremum, and so we're defining it as the supremum, and we write that alpha is the supremum of E, sup E. Okay, we say A is equal to the sup E. Similarly, for lower bounds, if we have some greatest lower bound, so there's a lower bound such that no number greater than it is now also a lower bound, then this is called the infimum of the set E. Okay, great. Let's go back to those sets that we were discussing before. We had the set A, which was this was the set we were talking about with the square root of 2, right? We have the set A. It's rational numbers such that their square is less than 2, and the set B, rational and positive rational numbers such that their square is less than 2, and the set B, rational numbers such that their square is greater than 2. Then the set B represents the set of upper bounds for A in the rational numbers. So B is the set of all numbers that are upper bounds for A, right? Because A has to have square less than 2, and B has to have square greater than 2, so it's rational numbers with the square greater than 2. So this obviously has to be an upper bound. It's bigger than even the smallest number in B is greater than the greatest number in A. Therefore, every B is an upper bound of A. However, B has no minimum value. We already proved that in the rational numbers. In the real numbers, it has a minimum value, right? We know it's the square root of 2. But in the rational numbers, B has no minimum value, and in fact, and it has it also has no infimum, right? Has no infimum, and A has no supremum in the rational numbers. So it is possible that you can actually that the supremum does not exist, and the infimum does not exist in the set, right? We can have a set where the supremum does not exist or the infimum does not exist. So this is going to be a key point, and this is going to be the reason why we have the next definition that we'll get to in a moment. Okay, so we want to know the conditions under which the infimum and the supremum exist, because we've just shown that it's not necessarily the case that they do. But let's now show a case where the infimum and supremum do exist, okay? So let C be the set of rational numbers such that the value, the rational number, is less than 0, so it's negative. And let D be the set of rational numbers such that the rational numbers are less than or equal to 0. So 0 is a rational number, right? So we have the set of all rational numbers. C is the set of all rational numbers that are less than 0. D is the set of all rational numbers that are less than or equal to 0. Well, then the supremum, so the least upper bound of C, of the set C, is 0, and the supremum of D, the least upper bound of D, is also 0. So for both of these sets, they both have a supremum that is equal to 0. However, notice that 0 is not in C, but 0 is in D. So you can have a case where, so this set C does have a supremum, great, but it doesn't contain its supremum. So the set does not have its supremum inside of it, whereas D has a supremum and its supremum is in its set. And in this case, we would actually call it a maximum, right? The maximum value of the set is 0 because it is the supremum and it's contained inside of the set. Great. Okay, so now I mentioned before up here in our red example that we had, the example in red, we saw that we do not always have a supremum, right? Some sets do not have a least upper bound. But in this other case in black, they do have obviously some sets do have a least upper bound. They do have a supremum. So we want to have some conditions under which the supremum exists, right? We want to say, okay, we want to focus on examples with the black example here, right? So we can say, by definition, an ordered set is said to have the least upper bound property. That means it has a supremum if the following is true. We say if E is a subset of the set S, E is not empty, so we have this property. It's a subset of S. It's not empty. It's not the null set, right? The empty set. And E is bounded above. Then the supremum exists in S. Okay? So then we have a least upper bound. If these three things hold, and it follows that we have the least upper bound, then we would say that the set S has the least upper bound property. So this set C, and this set D, they have the least upper bound property, whereas this set and this set do not necessarily have the least upper bound property. Therefore, because of that, we can say that Q does not have the least upper bound property. It's not guaranteed that if you have if you're dealing in the rational numbers, it's not guaranteed that there is a least upper bound. Therefore, the set Q does not have the least upper bound property because we cannot guarantee it. The real numbers do have this property. So the real numbers do have, we always can say that there is a least upper bound. So the ordered set S has the least upper bound property if all of those things are true. If it's if being a subset of it, a non-empty subset of it, is bound and having an upper bound, and the supremum exists, all of those three things, then it is said to have the least upper bound property, right? If it follows that the least upper bound exists, then it has this property. The real numbers have that. the real numbers have the least upper bound property, because it's guaranteed that if you have those, if these three things are true, then the supremum exists in the real numbers, but not in the it's not guaranteed in the rational numbers, as we already saw from the red example. Okay? Great. Now, let's get to a theorem. So now we're actually going to start proving things, right? So we've built up some definitions, and now we want to be able to use those definitions and see what things follow from them. Right? What things follow from the definitions? The theorem is, suppose that we have this ordered set, so that tells us something already. We have a definition of what an ordered set is. Has the least upper bound property, right? Well, we already said that we by definition, if it has the least upper bound property, it's an ordered set. So we don't really need to say that it's an ordered set here. But suppose S is an ordered set and it has the least upper bound property. Suppose further that B is a set that is a subset of that set S, that ordered set. So B has to be ordered, right, because it's a subset of S. And B is not empty. And furthermore, B is also bounded below. Okay, so we have the following things. We know that that S has the least upper bound property, and we know that this particular subset of S is bounded below and is non-empty. We're going to let L be the set of all lower bounds of B. Okay, so we know that we know that this set has some least upper bound in S. Okay, it has some least upper bound in S. We also know that L is the set of all of the lower bounds of B. Then all of these things have meaning, right? Then we can conclude that alpha, we can choose some number, we'll call it alpha, is the supremum of L, so the least upper bound of L. We know that alpha, we have this number alpha, it exists in S, and which is kind of trivial to prove, but we'll prove it anyways. And furthermore, alpha is that number, that least upper bound of L, is also the greatest lower bound of B. It's the infimum of B, and furthermore, alpha exists in S. Well, obviously, we already said alpha exists in S, so that'll also be trivial to prove once we've proven this part. Okay, so let's do the proof. Let's get into the proof. Since B is bounded below, it's clear that L is not the null set. It's not empty, right? L is the set of all of the lower bounds, and we just said that B is bounded below. So because of those two things, then L can't be empty. It's impossible that it's empty because B has a lower bound, right? We're saying by definition B is bounded below means it has a lower bound, and if L is the set of all of the lower bounds, then obviously if B has a lower bound, it can't be an empty set, right? Great. Then we're just defining what L is. It's the set of all numbers in S such that that they are less than or equal to all the numbers in B, right? This is just the definition of a lower bound anyways. So any number that's less than or equal to all of the numbers in B is a lower bound of B. So this is the set L. Great. Then every X in B is an upper bound for L. Well, yeah, that's kind of trivial to see, because then every X in B is greater than every number in L, right? We've already established this. So L must be bounded above, right? It has to be bounded above because we know that every value in the set B has to be bigger than every value in the set L. Great. So L has to be bounded above. So we know that L is the set of all the lower bounds of B, and that means that since it's all the lower bounds of B, they have to be smaller than every value in B to be a lower bound by definition. Therefore, L is bounded above. Great. And and since B was non-empty, which we said up here in the theorem, we started by saying B is non-empty. Then L has to have an upper bound because B is not empty, right? So L has an upper bound. Great. Now we already know that L is part of the set S, B is part of the set S, and we started off by saying S had the least upper bound property. Okay, so because of that, then L has a supremum because of the fact that S has some least upper bound property, which we can call alpha. So this was pretty trivial up to this point. Very simple reasoning, just going off of the definitions directly leads us to the fact that we have alpha is equal to the supremum of L, right? It is the least upper bound of L. We're just calling this the least upper bound of L. That part of the theorem is quite trivial to prove, right? We just based on all of the definitions, it led us to here. Now, the next part that we want to prove, we want to show that WTS is what we'll often use in that case. We want to show now that also alpha is the greatest lower bound of B. Okay, so this is a little less trivial, although it's fairly straightforward to also prove this. So by the least upper bound property, we know that if gamma is less than, so if we have some number that's less than alpha, then gamma cannot be a least upper bound, right? Because alpha is the least upper bound. So anything smaller than it is not an upper bound. Okay, so gamma is not an upper bound if it's smaller than alpha, because alpha was the least upper bound. It's the smallest upper bound. So that means that gamma is not an upper bound of B, is not an upper bound of L, right? It can't be an upper bound of L because it was smaller than alpha. Great. But we already said that every value of B is an upper bound of L, right? Every value of B is an upper bound of L. So that means that this value gamma that's smaller than alpha cannot be in the set B, okay? Then, following from that, it implies that alpha is less than or equal to every x that's in B. So it's less than or equal to every value in the set B. Great. We already sort of knew this, but it follows based on all of these definitions that this has to be true. Alpha is smaller than every value in X. Now the next thing is it follows by the definition of L. So we defined L as being the set of upper bounds, that alpha has to be in L. Okay, so alpha is an upper bound. A lower bound. Sorry, excuse me. Alpha has to be a lower bound of B, so alpha has to be in L because L was the set of all lower bounds of B. And since alpha is less than or equal to every value in B, that makes it a lower bound of B, right? It has to be a lower bound of B. That means that alpha is in the set of all the lower bounds of B. Great. So this greatest upper bound alpha of L. L has some greatest upper bound, right? Has to be in the set of L because it is a lower bound of B, as we already just proved by this line of reasoning, right? Great. So we know that it's in the set of lower bounds of B. Now, since alpha is the least upper bound of L, then if we have some number beta that's greater than alpha, then beta cannot be in L, right? So beta cannot be in L. This I hope this is clear. Beta cannot be in L because if beta is greater than alpha, well, we already said alpha is the smallest upper bound of L. If I have this is probably the trickiest part of the reasoning, but if beta is greater than alpha, and alpha is an upper bound of L. Now, beta can still be an upper bound of L, right? It's greater than alpha. So since alpha is the smallest upper bound, beta can still also be an upper bound of L, but it cannot be a member of L, right? Because alpha is already a member of L. You can only have one member of L that is the upper bound. Then that is an upper bound. Every other upper bound cannot possibly be a member of the set L, right? Anything bigger than the least upper bound cannot be a member of the set L. By definitionally, this is true. By the definition of upper bounds, if there is a least upper bound and you're bigger than the least upper bound, you can't be a member of the set, right? So that means that beta cannot be a member of L. Beta is not an L. Excuse me. Now we've established beta cannot be in L. Then beta can't be a lower bound of B, because if beta is not in L, it's not a member of L, then it can't be a lower bound because the definition of L was that it was the set of all lower bounds of B. So beta can't be then therefore a lower bound of B. Thus, alpha it's a lower bound of B. We already know this. And it also has to be the least. It's a lower bound of B. It also has to be the greatest lower bound of B, which gives me the infimum, because there can't be some number greater than alpha that's also a lower bound of B, as we've just established, right? So therefore, alpha is equal to the inf of B. So basically, we've taken all of these definitions that we've already learned up to this point, and we can prove that this must be true, right? If we know that S is an ordered set with the least upper bound property, B is a set that is a subset of S, it's non-empty, and is bounded below, it follows, and L is the set of all the lower bounds, it follows that the supremum of L is also the infimum of B. Okay, great. We'll actually be able to use this theorem down the road. That's all that I have for today. Thanks for joining me. See you again soon, I hope.